a value with an equal sign and you just blindly start using it, like printing it out or doing math on it, you might be manipulating a garbage value, which is some number that's essentially remnants of your computer having been on for a while. Because if you're using this canvas and reusing it again and again, surely there's going to be patterns of zeros and ones there that you didn't put there yourself, at least in the moment. They might be remnants of the past. So garbage values are values of variables that you did not proactively set yourself as intended. So we can actually see this. Let me actually go ahead and whip up a really quick program here after shrinking my terminal window. Let me close memory.c. Let me go ahead and open garbage.c. And in here, I'll do include, how about standard io.h. Let's include standard lib.h. Actually, we don't even need standard lib.h. Let's go ahead and include standard io.h and then int main void. And then inside of the curly braces, let's give me like a really big array of scores, like 1,024 scores, like if it's a really busy semester. And then let me go ahead and just blindly iterate from I equals 0 on up to I is less than 1024. And I'm not going to bother with constants. I'm just going to play around with these numbers for a moment. Oh, thank you. Oh, cookies for you. OK, these are, OK, here we go. OK, come on up. Thank you very much. Oh, fair is fair. OK. OK. OK, now everyone's really paying attention. All right. So in my loop here, I'm just going to do something stupid like print out all of the values in the scores array using %i, even though I did not put anything in this array. So on line 5, I'm obviously declaring an array of size 1024 for that many ints, but I'm never actually putting values in there myself or with getInt or any other function. So there's garbage values there. There's presumably 1,024 garbage values there, and we can now actually see them. Let me make my terminal window bigger. Let me make garbage, no pun intended, /garbage, and there's going to be way more than even fit on the screen, but who cares? We just need to see a few. There are some of the garbage values in the array. So make super clear that when you create variables of your own, you do not give them values of your own. Who knows what may be there? In some cases, it gets automatically initialized for you to all zeros, but that is not always the case. And in general, distrust the variable unless you yourself have put a value there. So how now might we leverage this to discuss, how now might we think about potential problems? Well, consider this code here, which this program too is more for discussion than actual utility, where at the top of it I declare a variable called x and a variable called y, both of type pointer. So x and y are supposed to be the addresses of two integers. Malloc, the size of an int and stored in x. So I'm giving myself space for x, even though obviously I could have done this weeks ago by just not using the star and just say, give me an int x. Now I'm doing it the low level way, mallocing the x for myself. I'm then saying, go to x, go to that address in memory and put the number 42 there. I'm then saying, go to y and put the unlucky number 13 there. But what's worrisome about this line here? After this line, this line, this line, something's bad, I think. Yeah, I never allocated memory for y. So specifically, I never assigned y a value, which means it's a garbage value, which is still a number. Maybe it's 0, maybe it's a big number, maybe it's a negative number. And if it's a positive number, it could be an actual address, like somewhere in the computer's memory. But *y means go there. Who knows what memory I'm touching? That's how computers crash if you touch memory that you're not supposed to. So let me pretend that I didn't at least do this. And let me just forge ahead and set y equal to x. So there's the same. And I think what that would mean is now if I do *y and go to the address, that's the same thing as going to this address in x. And I think this will have the effect of changing the 42 to 13. So this code is correct so long as I don't blindly dereference y by using *y notation. So this gets a little abstract, even though this is just an exercise here. And our friend Nick Parlanti will take a look at, whereby if I go ahead and open up this file, we'll be introduced to someone who's a little famous in the world of computing named Binky. If we could dim the lights and take a look at what bad things can happen if you don't manage your memory properly.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers? Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So are we going to switch places now? Oh, look, we're out of time. But...
All right, so our thanks to Nick. Can only imagine how many hours he spent making that happen, but hopefully it gives you more of a visual as to what's happening when we're dereferencing these addresses and going to them and assigning values, and when, as per Binky's explosion there, what happens when you dereference values you shouldn't. So related thereto, let me do this. Let me go over to VS Code and open up now a program I wrote in advance called swap.c. And the purpose of this program is just to swap the value of 2 variables. So let me walk over to the code here and point out that in main, I've got 2 variables, x and y. No pointers, no magic there, just x and y are 1 and 2 respectively. I've got a couple of printfs here saying x is %i, y is %i, passing in x and y, just so we can see that x and y are indeed 1 and 2. I'm then calling a function called swap, which presumably should swap the 2 values. And then I'm just printing the exact same thing again. My hope being that it's first going to say 1, 2, then it's going to say 2, 1, thus achieving the idea of swapping here. And here's swap. Swap takes in 2 integers, a and b, though I could have called them whatever I want. It temporarily puts a in temp. It then changes a to b. It then changes b to temp. And then that's it. It's a void function, so it doesn't return anything, but it does all of the mathematical work in here. So this is curious, though, because when it runs, let me open up my terminal window here, make swap, /swap, I should see 1, 2, and then 2, 1, but no. Even though I do think this is logically correct. And actually, we're almost out of stock, but we do have another box of cookies here. Can we get one volunteer to come on up here? Maybe, OK, how about you? Yes? In the pink, come on up. A round of applause, though really it's about the cookies now, I know. OK. And what is your name?
My name is Caleb, and I'm a first year concentrating in computer science.
All right, welcome. Please have us stand behind the desk here. So we have 2 no, you can stand, that's fine. Okay. We have 2 glasses of water, colored blue and orange respectively, and I would like you to swap the values of these 2 variables so that the orange liquid goes in the blue glass and the blue liquid goes in the orange glass.
Seems like a bad idea.
Why is that?
because I can't get one out to put the other one in because there's no third glass.
OK, correct, because we do have what we generally call a temporary variable here. So here, let me give you a variable called temp. And if I give you this, how does that change things?
Well, now I can take one
OK,
very carefully.
nice.
I'm trying.
OK,
There we go.
and now you can put B into A, if you will. Nice. And now temp goes back into that one. All right, that was very well done. Maybe a round of applause. Thank you. So this was just a cookie-based way of making clear that like the code on the screen seems to work. If I scroll back down to the swap function, it seems to do exactly what you just did there, whereby the temporary glass is where we put A, then we changed A to contain B, then we changed B to contain what was originally in A but is now in the temporary glass, and now we're done. So it did achieve the stated goal. And yet when I ran this code a moment ago, it was 1, 2, and then 1, 2 again. So why might that actually be? Well, here we can go back to some of today's fundamentals to consider what it is that's going wrong. And in this case, it's actually related to a concept we introduced some time ago, whereby there seems to be an issue of scope, whereby sometimes when you're manipulating variables inside of curly braces, thus defining their scope, it has no effect on values elsewhere. The variables might not even exist elsewhere, as we saw in the past. So what do I mean by this? Well, with scope, it turns out, or with matters of scope, it turns out that in this case, the way I've implemented the swap function, I'm doing something a programmer would call passing by value. I'm literally passing in x and y by their values, 1 and 2. Another way of putting this is passing by copy. So when I pass x and y into the swap function, it turns out a swap is actually getting copies thereof. Now, what do I mean by this? Well, let's go back again to this picture of memory representative of what's in your Mac, your PC, or your phone. And if we zoom in on this chip, and we treat it more abstractly as this canvas, get rid of the actual hardware, and consider what's going on inside of the computer, it turns out that there are conventions of how computers use this memory. And it's worth having a general sense of what goes where. So generally speaking, if this is a big rectangular region of memory, even though this is just an artist's depiction thereof, it turns out that the top of your memory, so to speak, is where machine code goes. The zeros and ones that you compiled get loaded into here. So when you do /something, or on a Mac or PC, when you double click, or on a phone, when you single tap, that loads your program's machine code, the app's machine code, to the top of your computer's memory. Strictly speaking, it doesn't have to be the top, but for our sake, it's in this region here. That's how the computer can access all of those zeros and ones quickly. Below that, so to speak, are where global variables go. We haven't had many occasions to use these, but if you define a variable outside of main and outside of every other function in C, it's what's called a global variable. So those get tucked specially up at the top so that they're accessible everywhere else in your program. Then there's something called the heap. More on that in a moment. And it grows downward. So you have a lot of memory available to you here in the heap, and you can keep getting more and more and more available to you. But at the bottom of this memory is what's called the stack. And the stack actually grows, curiously, in the other direction, up and up and up. And it turns out when you use malloc and ask the computer for memory, it comes from this heap region specifically. When you use functions with variables and arguments, you're using stack memory. Now, the astute viewer will notice that this does not seem like a good thing if they're about to collide eventually. And bad things can and will happen when one overflows the other, but more on that too in a moment. But let's focus for the moment on a stack when we do something like this swap function. So for instance, when we had code like this, which was bad, it did not allow us to permanently change the values of x and y. Why? No pun intended. Here on the stack is where the very first function goes in your computer's memory. So main, if you have any variables, they go at the bottom of the computer's memory once you've loaded that program. So what do I mean by that? Well, if you think back to the code a moment ago, it was things like x and y and so forth. When main calls swap, swap goes above it on the stack, so to speak. And each of these rectangles, the technical term is frame. So this is a stack frame, this is a stack frame, and if swap called another function, another frame would go on the stack this way. And then as soon as swap returns, though, that memory essentially goes away, or the computer forgets about it, even though the bits are obviously still there. You still have the hardware, but it's forgotten. And main remains until main finishes and exits your program. But let's consider what's going inside of these stack frames. So here's main at the bottom, and it had two variables, x and y. Those variables were 1 and 2, respectively. Main called swap, which had two arguments, a and b, also integers, which are effectively local variables also, even though you're declaring them in the signature, the prototype of the function. So when swap is called, swap is using its frame of memory as follows: room for a, room for b, room for temp. Not necessarily to scale. I just wanted everything to be a pretty rectangle. What's going where? Well, because functions in C pass values by value, that is copy. A is a copy of x, and b is a copy of y. But they're separate bytes. This is a different memory location than this. This is a different memory location than this. So we're just copying the patterns of bits from one to the other. This is passing by value, aka passing by copy. So what then happens? Just like our demonstration, we used temp cleverly, whereby with this code here, we copied the value of a into temp. So that puts the number 1 here, too. We then changed a to equal b. So that's what happened here. We then changed b to equal temp. So that changed the value there. But then swap returned. You went back to your seat, leaving a and b swapped, yes. But what was not swapped was x and y. Like, you did all of this work correctly, but in the wrong scope. You operated on copies thereof. So this swap function, while logically correct, will never solve this problem correctly as written because we've been passing by value. So today we introduce a technique whereby you can pass by reference instead, pass by pointer instead. Because instead of just passing in copies, what if we actually tell swap where x is and where y is? Not what it is and what it is, but where each is. Then swap can sort of follow the proverbial treasure map, go to those locations, and change them permanently. So this was the bad code in red. And this is going to escalate quickly visually, but it's just an application of today's ideas. This is the correct solution now. So let me do before in red is bad. Green after is correct. Why? The way you specify pass by reference or pointer instead is you change swap to take not two integers per se, but two addresses of integers. And the syntax for that today is just to add this star. So int star and int star. Meanwhile, the code down here has to change. Temp does not have to change. Temp is still just a variable that's ready for some value. But the A and the B need to be rewritten as follows. So star A means go to the address A and get its value and put it in temp, just like you reached for one of the glasses and poured it in. Star B means go to the value in B and grab it, and then go to the value at A and change it to be that at B. And then lastly, this is not now sweat, this is now colored liquid. This last line is go to the address B and put temp there instead. So the picture now is fundamentally different. Main looks the same still, but when swap is called effectively, and we won't bother with OX 1, 2, 3, or 4, 5, 6. Let's just do it with arrows pointing at things. A is a pointer to X. B is a pointer to Y. So what do those lines of code tell us to do? Go to A. So that means this, kind of like the old Chutes and Ladders game if you ever played, like follow the arrow, and that leads you to the number 1, and store it in temp. So that one was straightforward. Go to the value in B. So follow the arrow, that gives us 2, and put it at the location in A, which means put the 2 there. The very last line of code now means get temp, which is obviously there, and go to the address B and change it to 1. So now, even though we've not changed A and B at all per se, we've used them as little breadcrumbs to lead us to the right location in the computer's memory. So when swap returns this time, even though it's a void function, it has made a difference. And it's had this effect of swapping the actual original values of X and Y. The code admittedly is cryptic looking. It's not the most user-friendly syntax, but this ability now to go to locations in memory and change what is actually there is what we've been given today with this new syntax of the star operator and occasionally, as needed, the ampersand one as well. Questions on this technique, which is admittedly like the most sophisticated of the examples thus far, and will probably take time to get used to. Yeah? I say that again. Will this work if? Good question. Will this work if you're swapping the values of two strings instead of two ints? Yes, if you go to the address that the string represents and change, maybe with a loop, all of the characters one at a time. So it's going to be more complicated than this in green because you're going to have to change all of the individual characters, probably reusing a temporary char instead of a temporary integer. But you could. Yeah? Since integers have a fixed number of bits, can you ever run into a situation where you run out of memory? Absolutely. Like your phone, your laptop, your desktop can only do so much, can only count so high because of these physical limitations. And hopefully, it's just you never reach that limit. But we'll talk in a couple of weeks' time when we transition to web programming and databases and the Metas, the Microsofts, the Googles of the world that have crazy large amounts of data. Like the number of bits we use in those contexts is actually going to matter for exactly that reason. If business is booming and you've got lots and lots of data, lots and lots of users, you need to be able to count higher. Just so that you've seen the code actually in operation, here is, of course, my swap function down below. And if I go ahead and change its prototype to take in pointers to A and B, and similarly change the prototype up here, and if I go in and change A here to be star A to dereference it, star B to dereference it, star A to dereference it, and star B to dereference it, I claim now that this version of the code should now work. In fact, let me go ahead and do make swap. It didn't compile. So why might that be? Well, let me scroll up to see what the message is. Incompatible integer to pointer conversion, passing int to parameter of type int start. Like, that's a lot to absorb. But clearly, the issue is with how I'm calling swap. So why is this? Well, notice that now that my swap function expects as arguments pointers to integers, I can't just blindly pass in x and y, which are integers. Instead, I do need to use our friend, the new ampersand operator, to pass in the address of x and the address of y. So now if I reopen my terminal window, run make swap, and do /swap, now I see 1, 2, and then 2, 1. So the code changes in this way. And maybe this example, more so than others, makes clear why the star operator lets us go somewhere, but the ampersand effectively does the opposite and figures out what the address of something now is. All right, so what about these other locations in memory? Well, it turns out that indeed the stack, as we've described it, grows up and up and up. And recall that stack here in this sense is kind of like the stack of trays in the cafeteria or any of the dining halls. Like there's one tray, another tray, another tray, another tray, but then you start removing them from top down. So there's an ordering to them that we'll actually revisit next week. But this is not a good design. In general, like you shouldn't be doing things like two trains on the tracks, like barreling together toward each other in this way. But honestly, it's kind of the only way, because if you've only got a finite amount of memory, OK, sure, you could have them both grow in the same direction, but they're still going to hit some impasse eventually. You're still going to run out of space. So the way computers were designed years ago is they use memory in this way, even though bad things can happen. If you use too much stack space or too much heap space. So what do I mean by that? Our example a moment ago just had us call main and then swap, and that was it. So it's like 2 frames, no big deal. But if you call many functions again and again and again, if you do something recursively where you call yourself, you're going to pile stack frames potentially. So you could start to hit the so-called heap area. Meanwhile, if you call malloc too many times, you might be growing down, and then overrun some of the stack memory as well. So bad things can happen when you overrun either of these. And those of you maybe with prior programming experience might have heard at least one of these terms. Heap Overflow, or more popularly, Stack Overflow. Super popular website for questions and answers about programming. The etymology thereof is exactly this idea of overflowing the stack and touching memory that you should not, whether it's memory down here or even worse, memory over here, as by something called heap overflow. And these are specific examples of what we'll start calling buffer overflows. Buffer is just a chunk of memory. And buffer overflows means overflowing, using too much of that memory. And buffers are everywhere. In fact, if you've used YouTube recently, and maybe it's just kind of paused and spinning and spinning and spinning, maybe you're on a really bad connection, like there's no more bytes in your buffer. There's no more video footage in the buffer because maybe you have such a bad connection. But if Google were to make mistakes and try to download too many bytes at a time, they too could overflow a buffer. And if YouTube or similar apps have ever crashed, it could be because they're trying to use more memory than they actually should be. So these things are sort of everywhere. Now, as for these training wheels, we sort of took away the mystery of what a string is. But what about all of these other functions we've been taking for granted now for a few weeks? You can and should still use them to solve some problems because, frankly, C does not make it easy to get user input safely. Like, period, full stop. Like, it is very non-trivial to get user input without running the risk of overflowing a buffer. Why? Well, you're the programmer. How do you possibly know in advance how big of a string a human might type in tomorrow or the next week or the next day? You could try to be safe and allocate 1,000,000 bytes all at once, but what if they type in 1,000,001 characters or use copy-paste so much that they similarly overflow? So getting user input is a hard problem. So let's introduce you to what the alternative would be and give an appreciation for what libraries like CS50s and others like it are actually doing for you. Let me go ahead and create our own version of getInt and getString without using the CS50 library, but using a standard C function called scanf. And to do that, let me go over to VS Code. Let me create a new file called, for instance, get.c. And then in get.c, let's make a very simple program first that just gets an integer. But again, without using the CS50 library. So let me go ahead and include the standard IO library. Let me go ahead and declare main as int main void. And then inside of main, let me go ahead and declare an integer n so that we have some place to put the integer that we're getting from the user. Then let me go ahead and just prompt the user for a value for n. So n colon space, for instance, because again, I'm not using getInt, so I can't just call it to present the user with a prompt. So I'm going to use printf to create my own prompt. And now let me use this function scanf as follows. I'm going to call scanf, and then I'm going to pass to scanf, similar in spirit to printf, a format code like %i, effectively telling scanf that what I want it to scan, so to speak, from the user's keyboard is in fact a single integer. Now I'm going to close quotes, and I don't need a new line because I'm not trying to print anything. I'm trying to get something from the user using scanf, but I do need to tell scanf where to put this integer. Now, if I want to put this integer in the variable n, it's not quite as simple as just passing n in, because recall how variables are passed. This variable n is going to be passed by value. Effectively, a copy is going to go into scanf, and so scanf's not going to have the ability to change that value. But if you think back to how we swapped two values and passed two values into that swap function in C, well, if we pass those two values in by their addresses, so passing by reference, so to speak, then the function, swap in that case, scanf in this case, can actually go to that address and change the value. So to summarize, I'm going to pass to scanf one argument, which is a format code, and a second argument, which is the address of an integer into which to put the user's value. After that, I'm just going to go ahead and print out what's happened. So I'm going to go ahead and print out the value of n, followed by a colon, followed by an actual placeholder, %i \n, and I'm going to pass in now to printf the value n. So to be clear, I'm still passing n into printf just like we've been doing since week 1, but I'm passing to scanf the address of n so that scanf can actually go to that address and change the value of n. So I think this is actually going to work, even though I've not used getInt or any of the CS50 library. Let me go into my terminal, run make get. Seems to compile OK. Let me do /get. And let me type in a value like 50 for n. And indeed, I should see spit back at me that the value I got was 50. So it turns out that getting an integer from users is relatively straightforward just using scanf. But of course, to use scanf, you need to know a little something about pointers or addresses more generally. That was not knowledge we had in week 1. And so we do indeed use those training wheels of the CS50 library for the past few weeks so that we can get integers more easily. And it turns out if the user types more than a symbol integer, or even doesn't even type in an integer, scanf isn't necessarily going to behave as user-friendly as getInt might. So in the CS50 library, we do a bit more error handling for you as well. But let's consider now an implementation not of getting an integer, but getting a string instead. Let me clear my terminal window, and let me go ahead and erase all of this code, and instead focus this time on getting a string. Well, we know we can't use string anymore, at least if we're not using the CS50 library, but not a problem, because we know that strings are now char stars. So if I want to get a string from the user, that's like getting, I think, a char star. So let me just call this string s by default. Let me go ahead, therefore, and declare a variable s that's going to store my string. Let me go ahead next, as before, and prompt the user for the value of that variable just by prompting them with printf, so nothing fancy there. And let me try again using scanf to scan, this time, a string from the user's keyboard. I'm going to type scanf. I'm going to do %s instead of %i, because I indeed want to scan a string in this case. And then I'm going to go ahead and pass in just s. And here, at first glance, seems to be an inconsistency, because previously I did %n, but that's because n was an integer, not the address thereof. But in the world of strings, as we now know, a string is just the address of its first byte. And so if we declare s to be a char star, aka string, well, s is already an address. So I can just pass in s in this case to scanf without actually using an ampersand. After that, let's go ahead and print out the result. So let's just use printf. Let's print out a prefix like s colon again, %s as my placeholder, and now \n because I'm formatting it on the screen. And then let's go ahead and pass in s as always to printf. So s is just a string, so I just pass it into printf like that. Well, let me go ahead now. And I'm going to go ahead and compile this an old-fashioned way, because we actually protect you from doing something like this. But I'm going to go ahead and ignore the warnings you would otherwise see with make. And I'm going to go ahead and compile this with clang directly. So clang-o get, because that's the name of the program I want to output. But I'm also going to specify $W no uninitialized, which is simply another command line argument that's going to tell Clang not to warn us about variables that are not initialized. Because case in point, on line 5, as some of you might have noticed, I didn't actually initialize s to anything, even null. But that's OK, because I want to forge ahead blindly just to make a point as to what's going on here. And in fact, let's go ahead and compile this code as follows. It does seem to compile, even though make would have warned us that something's awry. Let me go ahead now and run /get, and this time not type in 50, but let me type in something like our familiar hi exclamation point and hit enter. I immediately get a segmentation fault, which means something has gone wrong related to memory. A segment of memory has been touched that I shouldn't have. Well, why in fact is this? Well, let's consider what it is we've been doing. If this here is my computer's memory, and in the first case I was just trying to get an integer, that was actually pretty straightforward. Because even if this memory is filled with a whole bunch of garbage values, as personified here by Oscar the Grouch, when I declared n to be an integer before, I just needed, on this machine, 4 bytes, which is the typical size for an int, and I put the number 50 there. So it doesn't matter that there were these garbage values. I just went to those 4 bytes after declaring a variable called n and overwrote those bits with some pattern of bits representing the number 50. But strings, we now know, are sort of fundamentally different. If I go back to that same memory space and I declare s to be a pointer, that is a char star, well, recall that pointers are generally 8 bytes on modern systems. And so that's like taking 8 of these bytes from memory and calling it s. But the catch is, if I haven't initialized s to actually be a valid location, as via calling malloc, there are still garbage values there. That is to say, patterns of bits that maybe have been there always, but from some previous function that got called, or some other lines of code if this program were actually bigger. So it's just some garbage value is filling that variable s. The problem, though, is that in my code now, when I call scanf and I tell scanf to scan a string from the user and to put it at that location S, well, what is that location S? It's literally a garbage value. It's the equivalent of a foam finger pointing there, there, there. We just don't know because it's not a valid address. And so I get that segmentation fault here in my terminal window because I've not initialized S to be some known value. I get a segmentation fault because effectively I've accidentally touched memory that I should not, in fact, have done so. So how do we fix this? Well, clearly I need S to point at some valid chunk of memory, and I could do that using malloc. But frankly, in this case, I could do it even more simply by just declaring S to be like an array of characters, as we might have in week 2. So let me go ahead and clear my terminal window here. Let me go into get.c, and let's simply change what S is. Instead of a char star, which we know is what a string technically is, we can still implement strings as arrays of characters. That's certainly still true. So let me go ahead and do that. Declare S to be an array of, say, 4 characters. And in this case, I should have enough room for the H, the I, the exclamation point, and even that null character, the trailing \0. So now let me go ahead and build this. Make get. And because I'm not initializing something this time, I can use make as usual without getting yelled at, because I'm not yet doing anything wrong. Now let me go ahead and do /get enter. And in this case, it's ready to receive my HI exclamation point enter. And all actually seems well. Why? Because in this case, I actually had enough space for S. Because if I go back to my memory here, because I've now redeclared S as an actual array of 4 characters, that's like asking the operating system, for instance, for these 4 chars here. And certainly I can fit HI exclamation point and the null character into those 4 bytes. So there's not a problem. But there might be a problem if the I, or the user more generally, types in too many characters. So let me go ahead and run /get again. Let me type HI exclamation point. But just to get a little aggressive, let me kind of highlight that and paste it again, 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 and again. And really type very excitedly a pretty long string that is surely longer than 4 bytes. Well, unfortunately, I've only asked the operating system for an array of 4 bytes. So what's going to happen with all of those extra highs? They're just going to, by default, remain contiguous from left to right, top to bottom in the computer's memory, but they're going to end up, some of those characters, at locations I didn't ask the operating system for in this array. So if I go back to VS Code here, I've typed in a very long string, certainly longer than 4 bytes in total. Let me hit enter. And darn it, there is another segmentation fault. So in short, you are going to see these segmentation faults anytime you touch segments of memory, so to speak, that do not belong to you, that you didn't allocate space for as via an array or even via malloc. And this is going to be a fundamental problem with getting strings because I don't know in advance how long the string is going to be that the human's going to type in. Maybe it's 4, maybe it's fewer characters, maybe it's even more. So what's the alternative? Well, I could go in here maybe and allocate, I don't know, like 4,000 characters for S, but what if you type in an even longer string that's 4,001 characters or more? I might still have these memory-related errors, these segmentation faults. So one of the reasons then, too, that we provide you with the CS50 library, and in turn functions like getString, is that getString very, very conservatively walks through the user's input byte by byte by byte, 1 character at a time. And what the CS50 library is doing underneath the hood is as soon as it realizes, oh, the user gave us another byte, we in the CS50 library are constantly allocating and reallocating more and more memory using malloc for you and effectively managing the memory required for that string. So even though scanf exists, it's dangerous to use with strings. And even with integers, it turns out it lacks some of the error handling that the CS50 library has thus far provided. How do we actually go about solving this? The way getString actually works in the CS50 library is it kind of tiptoes. It gets 1 character from you and then checks if there's another one coming. Then it allocates more space for a second. If there's still a third, it allocates more space, more space, more space. So essentially what getString does is it uses malloc again and again and again, and it kind of lays the tracks down as you're typing in the keystrokes and hitting enter so that we never assume how many characters you're going to type in. We dynamically allocate just enough bytes for you, plus 1 extra, for the null character. And this is sort of a hoop that's just not fun to jump through when at the end of the day, all you want to do is get input from the user. So even with the training wheels officially off, it's going to be annoying to get strings from users in C, but it is easy with ints, with floats, with other data types, and frankly, we'll soon in 2 weeks pivot to Python, which takes care of all of these problems for us and manages our memory. But for now, we have one final to do beyond scanf, which is file I/O, which is a fancy way of saying input and output, because now that we know a little bit of hexadecimal, now that we know a little bit about pointers, we actually have some more functions available to us that will let us actually manipulate files on a computer's hard drive, like image files or text files or anything else we might want. Among the most common functions that are related to files are these here. fopen is going to be a function that lets you open a file. Doing in code what you might otherwise do by going to File, Open in a graphical program. fclose does the opposite. It's the way you encode, sort of click on an X and close a file. Nothing's going to happen visually, but it's how you give access to a program to the contents of a file. fprintf, it allows you to print not to the screen, but to a file. fscanf lets you read data not from the keyboard, but from a file. fread and fwrite are similarly used to read and write data from a file, but generally binary data, like images or something that's not ASCII or Unicode text. fseek is a function that lets you kind of move around in a file left, right, kind of like fast forwarding or rewinding through Netflix or similar when you want to jump to a different location in a video, or in this case, a file. And there's bunches of others as well. So to give you a sense of what you can do with it when it comes to manipulating files, let's write just a couple of final programs, for instance, that let us manipulate some of this code for us. In fact, let me go ahead and open up here in VS Code a new file called, say, phonebook.c. And in phonebook.c, we're going to implement now a version of the phone book like we did in the past. But in this case, we don't actually have a forgetful program that prompts the user with getString for a couple of names and numbers and then just forgets about them altogether. This version of the phone book is actually going to go ahead and save them persistently to a file for us. And for this, let me go ahead and open up just on my other screen here. Without flipping over just yet, let me go ahead and open up. Give me just one moment. So we have this ready to go. Let me go ahead and create the file, this program as follows. I'm going to cheat and save time by using the CS50 library because I do not want to get into the nuances of getting strings character by character, which itself will escalate too quickly. But let me go ahead and include the CS50 library, the standard IO library, and lastly, the string library for this particular case. In my main function now, I'm going to go ahead and open up a file called maybe phonebook.csv. If you've ever used a CSV file, it's like a lightweight spreadsheet that you can open in Apple Numbers, Google Spreadsheets, Microsoft Excel. But CSV means that we're going to separate all of the values by commas. So anywhere we want a new column, we actually use a comma, as we'll soon see. So how do I actually do this? I can open a file called phonebook.csv by literally using fopen, phonebook.csv. And I have to tell fopen how I want to open it. Do I want to open it for reading with R? Do I want to open it for writing with W? Or do I want to open it with appending, A? And for something like a phone book, if I run this program again and again, I'm going to actually do append so that new contacts get added to the file and we don't overwrite it with W. Now, what does fopen return? It technically returns a pointer to a file. But this one's a little weird. It's all capitalized, but it is a thing in C. A file in all caps, star, file is going to be a pointer to that file in memory. So think of fopen as opening the file and returning the address thereof in the computer's memory. All right, what do I want to next do? I want to go ahead and get two strings from the user, like maybe someone's name, using getString, again, to keep things simple for now. Let me then go ahead and get another one. How about their number? Using getString again, prompting for number. And I don't strictly need these training wheels, so even though it doesn't really make a difference, I'm going to at least change that to char star, even though I do want to keep using getString conveniently. And now I want to save this person's name and number to that CSV file. So I'm going to use not printf, but fprintf, printing to that file variable, which is open in the computer's memory. Now I'm going to go ahead and print out two strings, %s, comma, %s. Then I want to go ahead and print out the name for the first placeholder and the number for the second placeholder. And for good measure, I want to move the cursor to the next line in the file. So I am going to include a \n. Then I'm going to go ahead and fclose that same file with fclose. And that's it. No more printing to the user. But I claim that I'm going to be changing the file again and again and again. So let me try this. Make phonebook, OK, /phonebook. Enter, and let's type in like David, and how about +1 617 495 1000. Enter. OK, hopefully it worked. Let's do it again. /phonebook. Carter, we'll give him the same number as last time. 495 1000. And let's do, how about just those two? So let me go ahead now and reveal that we do have a file in here called phonebook.csv. So that does exist. Let me go ahead and do this. Let me open up my file browser over here. I've got a lot of files I've created. Here's phonebook.csv. And if I click on it, there is the file that I just created, separated by commas. But even more interestingly, let me actually right-click or control-click on this, download it to my Mac's Downloads folder. Let me go into my Downloads folder just for fun, and I've installed in advance Microsoft Excel. If I go into my Downloads folder and open up phonebook.csv, we're going to see, oh, Apple numbers, not Excel, opening up, view my spreadsheets. All right, numbers is kind of stupid. So there we go. No, just this isn't a Mac versus PC thing. So now we have phonebook.csv rendered in this format here. Numbers presumes that the top row should be gray and not white as well, so the formatting looks a bit off. Anyhow, clearly you could open this same file in a spreadsheet program like Microsoft Office or Apple Numbers, or of course something like Google Spreadsheets. But let me do one other thing when it comes to copying files now, whereby besides making a phone book, whereby I clearly have the ability now to save strings in files. And actually, just for good measure, let me hammer home the point that anytime we're dealing with pointers now, something could go wrong. And if you read the documentation for fopen, we should also check that file could be null. Maybe the file's not found, or something's not working on the server. And so, you know what, just to be safe, we should return one there. So even not just malloc, not just getString, anytime a function returns a pointer, you should check if it's null, because if it is, per the documentation, almost always means something has gone wrong. So you should get out lest you trust the return value therein. So let me go ahead and do one other program here. Let me create my own copy program. So up until now, we've used commands like rm and ls and cp for copy. I can actually create my own version of Linux's copy program, perhaps as follows. Let me actually go into cp.c in this case. Let me include some familiar files, standardIO.h. Let me include, how about one other, standardint.h, for reasons we'll see now. Because in standardint.h is that uint8 type that I mentioned earlier, which just means give me